In this lecture, we will study these two concepts. We will study what is this what is this strongly connected component in directed graph, what is this concept, and what is this concept adjacency matrix and adjacency list. Okay, adjacency matrix and adjacency list. So this concept we will study. So let's start now. Before we start, let's see for undirected graph what is connectedness and what are components. You already know. If you have undirected graph, then what are the components? Components are like islands. I told you components are like islands. So this is an undirected graph. In this graph, tell me how many components are there. Tell me how many. What is the number of components? What is the number of components? Number of components, or we call them number of connected components. See, this is same as number of connected components. Component is same as number of connected, because every component is a connected. Every component is connected, right? Every component is a connected graph. Like this component, this is the component, and this is connected graph. So I can say number of connected components. So both things are same. Remember, both things are same because every component is a connected graph. Every component is a connected graph. Okay, every component is a connected graph. So I can say number of connected components is 2. So this is the concept for undirected graph. You know, for undirected graph, this is very easy. For undirected graph, what is a component? Component is like, I can say component is like a island. We have already seen this. Okay, so for connectedness in undirected graph, this is straightforward. I can say like this graph. If you look at this graph, just look at this graph. If you look at this graph, then you can notice that this and this, they are not connected. You can clearly see this and this, they are not connected. You can clearly see there is a gap. There is a gap. Okay, they are not connected. So this is the idea. Very simple. So I can say a graph that is not connected is obviously disconnected in components. So this is a component. This is a component. So total 2 components you have. Okay, so this is the definition. You know, when can I say graph is connected? What is the definition of connected graph in undirected? When you have undirected graph, for undirected graph is connected if for every pair of vertices there is a path. Between every pair of vertices there is a path. And I can say else the graph will be disconnected. Okay, so for example, this graph, look at this graph. This graph is disconnected. But if you look at this graph is connected. Okay, in this graph, between every pair of vertices there is path. Whatever 2 vertices you take any 2 vertices, there is a path between them. So this is a connected graph, and this is a disconnected graph because there is no path between a comma f. There is no path. And you can notice in this, so this is disconnected. In this, how many components you have in this graph? How many components? Total 2 components you have, this and this. Total 2 components. And in this graph, how many components? 1 component. Okay, so you can notice a graph is connected if and only if there is 1 component. You know this concept. Okay, for undirected graphs, I am talking about undirected graphs. So for undirected graphs, you can notice that a graph is connected. I can say a graph is connected if and only if number of components is equal to 1. If and only if number of components is equal to 1. Okay, and a graph is disconnected. Similarly, I can say a graph is disconnected if and only if number of components is greater than or equal to 2. I can say number of components will be greater than or equal to 2. This is the definition. Okay, so this is the concept, very simple concept. You know, in this graph, how many components you have? In this graph, total how many components? 3 components you have. So you can notice this is a component, this is a component, this is a component. So total 3 components you have in this graph. Okay, so connected component, that is basically maximal connected subgraph. You know this concept. Okay, what is a connected component? What is a component? What is a component? Component is basically maximal connected subgraph. Maximal connected subgraph. Maximal connected subgraph. This we have already seen in the previous lectures. Okay, so these components are like islands, I can say, in the undirected graph. Okay, these components are like islands. I can say this is an island, this is an island, this is an island. Okay, like this. Now let's see in this graph how many components? Total how many components? Total 2 components you have in this graph. Okay, so very simple. In this graph we have total 2 components. So this is a disconnected graph. Now let's move on for directed graph. For directed graph, how can I say, okay, what is connected and what is component? How to define this for directed graph? See, this is different. This is very different. For directed graph, this is actually different. If I give you this directed graph, A, B, C, if I give you this directed graph, okay, consider this graph. What do you think? Is this connected? Is this graph connected? What do you think? Is this graph connected? What do you think? Think about it. Please think about it. Do you think this graph is connected? So remember, for directed graph, okay, like, okay, for undirected graph, you will think, okay, yeah, this is connected. It seems like this is connected, right? It looks like that this is connected because it looks like one part. Yes or no? It looks like one part, one part. It looks like one island. Yes or no? It looks like one island. Okay, it looks like one island. Similarly, this graph, is this graph connected? What do you think? This graph, is this graph connected? Just think about it. Is this connected? Let me tell you, the answer is no. Let me tell you, the answer is no. Because, okay, for directed graph, see here, if you notice, this graph, this is a directed graph. First of all, remember, this is a directed graph. Okay, this is a directed graph. In the directed graph, you can notice one thing, that we cannot go from C to A. Okay, there is no path. I can say there is no path. There is no path from C to A. You cannot go from C to A. There is no path from C to A. And because there is no path from C to A, so this directed graph, this is not connected. This directed graph is not connected. Okay. So because there is no path from C to A, we have no path from C to A. So remember, it looks like this is one part. See, where is, I know some of you might be thinking, sir, this is one part. This looks like one island. It looks like one island. It looks like one part. Okay, one part. It looks like one entity. It looks like one entity. But remember, this is not how connectedness is defined for directed graph. For directed graph, we don't define connectedness like this. Yes, this is one entity. I know. This is one entity. This is one island. I know. But remember, still this is not connected because you cannot go from C to A. There is no path from C to A. So that is the reason this is not connected. Actually, let me tell you one more thing. Actually, for directed graph, this word we don't use. We don't use this word. We use this word, that this is not strongly connected. This word we use, strongly connected. This word we use, okay, strongly connected. We don't use this word. We don't use this word, but we use the word strongly connected. Okay. But remember, by default, connected and strongly connected, they are same thing. For directed graph, by default, these are same thing. For directed graph, there is a concept of, we will study, don't worry, we will study. Okay, there is a concept of strongly connected components, or I can say strongly connected graph. Okay, strongly connected graph. Remember, by default, strongly connected graph, and I can directly say connected graph. Both are same. By default, when I say connected graph for directed graph, then that is same as strongly connected graph. So, okay, so this graph, if you notice, this graph is not connected. This graph is not connected, or I can say this graph is not strongly connected because we cannot go from C to A. We cannot go. Okay, so let's define it. Now let's see one by one. Don't worry, you will understand. Don't worry. Let's define first. Let's see for two vertices. Let's define how they are connected. Okay, two vertices are connected, or I can say two vertices are strongly connected. By default, connected means strongly connected. Remember this point. Okay, remember this point, that for directed graph, by default, connected. By default, this connected automatically means strongly connected. By default, connected means strongly connected. So even if I don't say strongly connected, by default, connected means strongly connected. Okay, by default. Now let's see this. See this definition. In a directed graph, your graph is directed. In a directed graph, two nodes are connected, or I can say two nodes are strongly connected if and only if there is a path from U to V and there is a path from V to A. Remember, there is a path from U to V and there is a path from V to U. Then we will say, means I can say there must be a path from U to V and there must be a path from V to U. This must happen. This must happen. This must happen. There must be a path from U to V, and there must be a path from V to U. This must happen. In this situation, if this situation happens, then we will say that U comma V are connected, are strongly connected, are strongly connected. Okay, then we will say that they are strongly connected. Means you can go from U to V, you can go from V to U. So tell me in this graph, okay, which two vertices are strongly connected? So find out, like, okay, strongly connected vertices. Which two vertices are strongly connected? Let's see. Let's see which vertices are strongly connected, or I can say which vertices are connected. Can I say vertex A comma, okay, can I say vertex A comma B are connected? Please tell me. Can I say vertex A comma B? Can I say they are connected? You can go from A to B. Can you go from B to A? Yes, you can go from B to A. You can go from B to A. Okay, so you can notice, you can go from A to B. You can go from B to A. Okay, so I can say yes, these are strongly connected. These are connected. What about A comma D? What about A comma D? Yes, you can go from A to D. You can also go from D to A. So they are also connected. What about this A comma F? What about A comma F? Tell me about A comma F. They are no, because you can go from A to F. You can go from A to F, but you cannot go from F to A. Okay, you cannot go from F to A. What about B comma D? What about B comma D? Yes, because you can go from B to D, and you can go from D to B. Okay, so these are also connected. What about these, like F comma H, or I can say F comma H? What about them? F comma H. You can go from F to H, but can you go from H to F? Can you go from H to F? No, so these are also not connected. F comma H, these two vertices are not connected. These are not strongly connected. What about G comma H? No, because you can go from G to H. There is a path from G to H, but there is no path from H to G. Okay, what about this F comma G? F comma G, again no, there is a path from F to G, but there is no path from G to F. So these are also not connected. These are also not strongly connected. Please let me know if anyone has any doubt. Let's see this B comma F. What about this B comma F? Okay, there is a path from B to F. There is a path from B to F, but there is no path from F to B. So these are also not connected. These are also not strongly connected. So the definition is very simple. Two vertices are strongly connected. Two vertices are strongly connected if you have a path from U to V, and you have a path from V to U. Okay, so then we will say that they are connected, or I can say they are strongly connected. Now one interesting question I will ask you. Very nice question. See this. In a directed graph, let's define a relation on set of vertices. Let's define a relation. We are defining a relation on set of vertices. We are saying that vertex A is related to vertex B if and only if A comma B are strongly connected. Okay, means two vertices are related. These two vertices are related if and only if they are strongly connected. Tell me one thing. Is this reflexive? Is this relation reflexive? Is this relation symmetric transitive equivalence relation? What is this? Okay, let's check it out. Let's check it out. Let's check it out on this graph. On this graph, let's check it out. Tell me, can I say A comma A? Can I say they are connected? Can I say they are strongly connected? Can I say they are strongly connected? Tell me. See, strongly connected. Strongly connected. Okay, strongly connected pairs. Tell me, A comma A, are they strongly connected pairs? Yes, because very trivial. These are trivially. Okay, trivially. You can go from A to A. Trivially you can go. Like you, okay, just don't walk. Okay, there is a path from A to A. Trivial path, I can say. Trivial path you have. Trivial path. Path of length 0. Path of length 0. Trivial path you have from A to A. Okay, so yes, they are strongly connected. Next, what about C comma C? What about C comma C? Again, the same thing. Yes, trivial path. Okay, there is a trivial path means length 0. Trivial path length 0. Okay, next, what about A comma B? A comma B. You can notice there is a path from A to B, and you can notice there is a path from B to A. There is path from A to B, and there is path from B to A. So I can say yes, they are also strongly connected. What about B comma A? What about B comma A? Yes, they are also strongly connected. Okay, because there is a path from B to A, there is path from A to B. Okay, next, tell me. So you can notice that A comma B, okay, they are strongly connected, and you can notice that you can also notice that B comma D are also strongly connected. Okay, A comma B is strongly connected. B comma D is also strongly connected. You have path from B to D. You also have path from D to B. So okay, these are connected. You can notice that automatically implies that A comma D are also strongly connected, right? Yes or no? Automatically implies that A comma D are also strongly connected. You have path from A to D. You have path from D to A. So they are also strongly connected. So this is the idea. I can say that on vertices, if you define this relation, then can I say this is reflexive? Yes, this is reflexive. Why this is reflexive? Remember, your graph, your directed graph, your directed graph G, V, comma E. Okay, you are defining a relation R. This relation R you are defining on set of vertices, and you are saying that a vertex U is related to vertex V if and only if okay there is a path from U to V and there is a path from V to U, means they are strongly connected. Okay, so this is the question. Now you can notice this R is reflexive. This R, this relation, if you notice this relation, this is reflexive. This is reflexive. Why this is reflexive? Because I can say that A is related to A trivially. Okay, I can say A is related, I can say A is connected to A trivially. Okay, path of length 0. Path length 0. Path length 0. Okay, next, are they symmetric? This relation, is this symmetric? Is this relation symmetric? And the answer is yes. The relation is symmetric also. Because see, very simple. If A comma B, if A comma B are strongly connected, then B comma A are also strongly connected. Very simple. It means you can go, there is a path from A to B, there is a path from B to A. It automatically means there is a path from B to A, there is path from A to B. So you can notice if this happens, I can say, if this happens, or I can say that if A is related to B, it means A is related to B, means if they are strongly connected, then B comma A is also strongly connected. What about transitive property? What about transitive property? Yes, transitive property is also true. Very simple. See, if A comma B are strongly connected, B comma C are strongly connected. Okay, if these are strongly connected, then what it means? See, then what it means? It means there is a path from A to B. Okay, there is a path from B to C. There is a path from B to A, and there is a path from C to B. So you can notice there is a path from A to C. You can clearly see there is a path from A to C. There is path from A to C. There is path from C to A. There is path from A to C. There is path from C to A. So yes, okay, they are also strongly connected. If A comma B are strongly connected and B comma C are strongly connected, then A comma C is also strongly connected. Very simple concept. Because you can notice that, okay, you can notice there is a path from A to C. This is the path from A to C, and this is the path from C to A. So this is transitive also. So I can say this is equivalence relation, reflexive, symmetric, transitive. So this is a equivalence relation, correct? Okay, this is a equivalence relation. Very simple. So yes, all these properties are there. Okay, so this is equivalence relation also. Now let's find out equivalence classes. If this is equivalence relation, then you find equivalence classes. Let's find equivalence classes. Let's find them. Let's find equivalence classes. Okay, let's find them. So in this graph, let's find the equivalence classes. What do you think? What are the equivalence classes in this graph? What do you think? In this graph, what are the equivalence classes? Okay, so let's find equivalence classes. Equivalence classes. Find out the equivalence classes. See, what is the equivalence class of A? Tell me the equivalence class of A. Please tell me the equivalence class of A. Equivalence class of A means to which A is related. To which A is related. See, A is related to A. You can notice that A from A to B and from B to A. You can notice A comma B are strongly connected. A comma B are strongly connected. A comma B are strongly connected. A comma D are strongly connected. Okay, there is a path from A to D. There is a path from D to A. So they are also strongly connected. What about C? Can I say A comma C are strongly connected? Can I say A comma C are strongly connected? A comma C. Can I say they are strongly connected? A comma C. You can notice, yes, they are strongly connected. You can notice they are strongly connected. You can go from A to D, C. There is a path from A to C. Notice there is a path from A to C. Notice there is a path from C to A. There is a path from C to A. So there is path from A to C. There is path from C to A. So finally, only one equivalence class you will get. Only one equivalence class. So for this graph, I can say for this graph, only one equivalence class. For this graph, only one equivalence class. Let me tell you one thing. What this equivalence class tells you? This tells you that every two vertices are strongly connected. Yes or no? Agree? Every two vertices are strongly connected. Every two vertices, if you take any two vertices, are strongly connected. Every two vertices are strongly connected. Every two vertices, whatever two vertices you take, those two vertices are strongly connected. So this is a strongly connected graph because every two vertices are strongly connected. So this graph is connected graph, I can say, because every two vertices are strongly connected. So that is the reason this graph, we call it a strongly connected graph. This graph is strongly connected. Let me tell you one more thing. In this graph, if you notice, there is only one equivalence class. This equivalence class is called a strongly connected component. Okay, let me just tell you that this equivalence class, every equivalence class, this equivalence class, every equivalence class of this strongly connected relation, strongly connected relation. So this relation that we have defined, okay, this relation that we have defined, right? So every equivalence class of this relation is called strongly connected component. Strongly connected component. That is called strongly. Don't worry, this will be clear. Don't worry. If you have any doubt with example, this will become clear. So do not worry about it. Now let's see. In this graph, on this graph, let's apply. How many equivalence classes are there? On this graph, let's apply let's find out how many equivalence classes. Find out equivalence classes. Let's find out equivalence classes. What are the equivalence classes? What is the equivalence class of A? See, equivalence class of A will have A. And you can notice one thing. Just notice one thing. Just notice one thing. This is a loop. If you notice, this is a loop. This is a loop. This is a loop. If you notice, it means there is a path from A to B. There is a path from B to A. There is a path from A to D. There is a path from D to A. There is a path from A to C. There is a path from C to A. So between any two vertices, there is a path. I can say here in this, every two vertices are strongly connected. There is a path from B to C. There is a path from C to B. So you can notice they are on a cycle. Okay, they are on a cycle. So I can say yes, they all are strongly connected. Okay. Oh, every pair here, every pair is strongly connected. What about A comma F? Tell me, what about A comma F? A comma F are not strongly connected. Yes or no? A comma F is not strongly connected. A comma G is not strongly connected. A comma H is not strongly connected. There is a path from A to H, but there is no path from H to A. So they are not strongly connected. So this is the equivalence class of A. We got equivalence class of A. Okay, and this is also equivalence class of B. This is also equivalence class of B. This is also equivalence class of C. This is also equivalence class of D. This you already know. Okay. So this equivalence class we got. Now let's find out equivalence class of F. What that will be? Equivalence class of F. That will be only F. That will be only F, because remember, okay, you can notice F comma H are not strongly connected. There is a path from F to H, but there is no path from H to F. There is path from F to G, but there is no path from G to F. So this is the equivalence class of F. What is the equivalence class of G? Equivalence class of G, that is G itself. And what is equivalence class of H? That is H only. That is H only. So in this, you can notice 4 equivalence classes we have. How many? 4 equivalence classes we have. Okay, every equivalence class. So okay, every equivalence class is basically a strongly connected component. You know this. So this is a strongly connected component. 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 Okay, because you can notice that this is a strongly connected component. This component in this area, look at this area. In this area, everyone is strongly connected to everyone. In this area, everyone is connected to everyone. Everyone is strongly connected to everyone. So this is strongly connected component. This is a strongly connected component. This is a strongly connected component. Tell me, is this a strongly connected component? Tell me, is this a strongly connected component? No, because G comma H are not strongly connected. There is path from G to H, but there is no path from H to G. Okay, so this is not a strongly connected component. So remember, every equivalence class is, I can say every equivalence class is basically a strongly connected component. Okay, so this statement we have already seen that every equivalence class of this strongly connected relation is a strongly connected component. Now you can easily find out strongly connected components. So what is a strongly connected component? Tell me, what is the definition of a strongly connected component? What is that? A strongly connected component is simply a set of vertices. This is the definition. A strongly connected component, SCC. What is that? A strongly connected component. So I can say this is a set of vertices. Please note the definition. Read the definition. Read the definition. What is a strongly connected component? A strongly connected component. This is a set of vertices. Remember, this is maximal set of vertices. This is maximal set of vertices, okay, which are strongly connected to each other. So this is the maximal set of vertices. This is a maximal set of vertices such that any two vertices are strongly connected. Okay, any two vertices, every pair of vertices is strongly connected. Every pair of vertices, there is path from U to V, there is path from V to U. This is the definition. Okay, so maximal set of vertices which are strongly connected. This is the definition of strongly connected components. Very simple definition. So you can notice, if this is SCC, if I say this is SCC, A, B, C, D, if I say, okay, for example, if SCC is this, a strongly connected component is this, what it means? Tell me what it means. It simply means there is a path from A to B. There is a path from A to B, and there is a path from, okay, B to A. Similarly, there is a path from A to C, and there is path from C to A. Similarly, there is path from B to C. You can note this is the path from B to C. So there is path from B to C, and there is path from C to B. You can notice this is the path from C to B. And similarly, there is path from C to D, and there is path from D to C. So this is the idea. You can notice. Now, okay, is there any path from A to D? Yes. This is the path from A to D. This is the path from A to D. And you can notice this is the path from D to A. So between any two vertices, okay, between any two vertices you take, there is a path. Every two vertices you take, there is two-way path. Any two vertices you take. And remember, if this is SCC, then this is maximal also. If this is SCC, then this is maximal also. What it means? This is maximal also. What this means? This means there is no other vertex. This means there is no other vertex. This means there is no other vertex. There is no other vertex E. There is no other vertex E such that this will happen. Such that this will happen. There is no other vertex such that this will happen. Okay, so this will not happen. Let's see this example. In this, you can notice, is this a strongly connected component? Please understand, tell me. Is this a strongly connected component? Yes. Okay, yes, you can notice this is a strongly connected component. This is a strongly connected component. This is also a strongly connected component. What about these two? What about these two? What about these two? Are they strongly connected? No, they are not strongly connected. They are not strongly connected because there is path from this to this, but there is no path from this to this. So in this, how many strongly connected components? Number of strongly connected component is 2. Is this a strongly connected component? Is this a strongly connected component? No, a strongly connected component is maximal. Remember, this is not a strongly connected component. This is not a strongly connected component because this is not maximal. Because this is not maximal. Okay, this is not a strongly connected component because this is not maximal. So number of strongly connected component is 2. Similarly, this is not a strongly connected component because this is not maximal. You must take maximal. You must take maximal. Okay, always take maximal. These are strongly connected vertices. A, B are strongly connected vertices, but this is not a strongly connected component. Please understand. A, B are strongly connected vertices. They are strongly connected, but this is not a strongly connected component. A, B are connected. That is fine. A, B are connected. Very good. No problem. But this AB, this is not a strongly connected component. Is this clear? Component. This component. Component means this should be maximal. Let's see this graph. In this graph, how many you see? How many components are there? A, B, C, D, E, F, G, H. Okay, let's see one by one. How to find out? Okay, please understand this method. What I'm going to tell you, please understand this. First, you find out what is the strongly connected component in which A is there. So first you find out a strongly connected component to which A belongs. To which A belongs. Find out the strongly connected component to which A belongs. So you can notice there is a cycle here. If you notice there is a cycle here. See, there is a cycle. There is a cycle here. So definitely these are in the, okay, so definitely these we have A, B, C, D. Can I put E? Please tell me, can I put E? You can notice that there is no path from E to A. There is no path from E to A. We don't have any path from E to A. You can notice there is no path from E to A. There is no path from E to A to F. Sorry, F to A. So okay, so this is the strongly connected component to which A belongs. So this we got. Now forget about it. This is what we got. You cannot add anything more. Remember, you cannot add anything more. So this is done. Now look at the remaining graph. Look at the remaining graph. Okay, strongly connected component of E. What is the strongly connected component of E? That is E, F. That will be E, F. You cannot add anything more. You cannot add anything. Okay, you cannot add anything more. So this will be your, okay, now forget about it. Next, you can notice there will be G. Next, there will be G. And next, there will be H. Next, there will be H. So total 4 components, connected components you have is in this graph. These are the 4 strongly connected components. Is this clear? Anyone has any doubt in this? Let's see another question. Let's see this another question. If I change this arrow, if I modify this arrow, let me modify this arrow to this side. Let me modify this arrow to this side. Now tell me the answer. Tell me the answer now. Let's find out the strongly connected component to which A belongs. Okay, so you can notice this A, B, C, D, because there is a cycle. See, there is a cycle. So A, B, C, D, A, B, C, D. Now let's see. Can I say, see, there is a path from A to E. Can I say there is a path from E to F, E to A? Yes, E also will be included. Now E also will be included. F also will be included. E comma F, they will also be included. Yes or no? Now E comma F also will be included because there is again a cycle. See, there is a cycle. See, there is a cycle. See, there is a cycle. So you can notice that this is the component. So finally, I can say that this component you got this component you got. Okay, one component, and the remaining is this component. So number of strongly connected components, that is 3. Okay, so very simple. This concept is very simple. Let's find out this question. Draw a 3 vertex graph with one strongly connected component. Can you do this? With one strongly connected component. Only one strongly connected component you must have. So you can draw this graph, A, B, C, this graph. In this graph, you only have one strongly connected component. In this graph, number of strongly connected component is only 1 because you have this cycle. So you can notice this is the strongly connected component. Number of strongly connected component is 1. Okay, 2 strongly connected component. Can you draw a graph which has 2 strongly connected component? Can you draw a graph? A, B, like this, C. Okay, so in this, how many strongly connected component you have in this graph? Number of strongly connected component, that is 2. Okay, number of strongly connected component is 2. This is a strongly connected component and this is a strongly connected component. 3 strongly connected component. What should be the graph? A, B, C. This graph will work. Yes or no? This graph will work. This graph will work. You can check it out. This graph will work because you can notice there is path from A to C. There is no path from C to A. There is path from A to B. There is no path from B to A. So finally, in this graph, this is a strongly connected component. This is a strongly connected. This is a strongly connected component, and this is a strongly connected component. So number of strongly connected components is 3. Okay, so like this. Yeah, that is also fine. 3 disconnected. This is also fine. Okay, how many for this graph? For this graph, how many strongly connected component? Number of strongly connected component is 3. For this graph, how many strongly connected component? A, B, C. How many strongly connected component? Number of strongly connected component is again 3. And okay, for this graph, how many strongly connected component? A, B, C. For this also, number of strongly connected component is 3. Is this clear? Here you have only 3 strongly connected components. In this is the strongly connected component, this is the strongly connected component, this is the strongly connected component. So is this concept clear? Strongly connected component. The concept of strongly connected component, remember this must be maximal. Please understand, strongly connected component, this should be maximal. Many students make this mistake. This should be maximal. Okay, maximal. Okay, and basically every pair of vertices, connected, strongly connected. Okay, every pair of vertices is strongly connected, and this must be maximal. So if I give you this graph like A, B, C, D, E, this graph if I give you, then tell me how many strongly connected components? Number of strongly connected component, how many? Very simple. Find out. Okay, this A is strongly connected to what? This A is strongly connected to whom? This is strongly connected to A. So you can notice this is strongly connected to B also. There is a cycle. There is a cycle like this. There is a cycle like this. So you can notice that these vertices A, B, D, E. Okay, so this is strongly connected. This is a strongly connected component. I can say this is as CC, strongly connected component, and there is another strongly connected component, that is C. So you cannot, this is a strongly connected component, and the remaining vertices, this is a strongly connected component. So this is your S1, this is your S2. Okay, so very simple. The concept is very simple. Remember one more thing, please remember this DE is this strongly connected component. This DE, this is not a strongly connected component because this is not maximal. This is not a strongly connected component. This component is not strongly connected. Let's see this graph, this question, and this is very interesting question. Before this, let me ask you another question. Before this question, let me ask you, if you have an undirected graph, let me ask you this question. Let's assume you have undirected graph. You have undirected graph G, in which, okay, you have undirected graph G in which you have number of vertices and number of components. Let's assume your graph is undirected. Let's assume number of components is K. Now tell me, okay, if, okay, let A comma B are two vertices. You have two vertices in this G. We add this edge. Okay, like there is no edge between them. Let A comma B be, okay, be two vertices such that they are not adjacent. A comma B are not adjacent. Let's assume they are not adjacent, means there is no edge between them. They are not adjacent. Now we add this edge. Now we add this edge. Now we add edge AB. This edge AB we add in G. Then tell me what will be the number of components. What can you say about number of components? Remember what we are doing? What we are doing basically you have undirected graph. In that undirected graph, you are adding one more edge. You have undirected graph plus one more edge. Plus one more edge you are adding. Only edge you are adding between existing vertices. Plus one more edge you are adding. Okay. Then if you do this, then what can you say about number of components? What can you say about number of components? Very simple. Number of components, either it will remain unchanged, either it will be K or it will be K minus 1. Either it will remain unchanged or it will reduce by 1. Very simple. Very simple. Either it will be K or it will become K minus 1. For example, consider this graph. A, B, C, D, E, F. Consider this graph. This is your graph G. Now, if I add this edge, okay, add one edge. What you do? Add one edge. So in this graph, number of components is 3. If you notice, let's add one edge. If I add this edge, then number of components is what? Then number of components, that is still 3. Yes or no? If I add this edge, number of components, that is still 3. Number of components, that is still 3. If I add this edge, okay, instead of this, if I add this edge, okay, let's not add this edge. Now let me add this one. This edge let me add. Now what will happen? Now what will happen? The number of components, the new number of components, that is K minus 1. That is 2 now. So this is the idea. Okay, if you add one edge, very simple. In undirected graph, if you add one more edge between the existing vertices, then either the number of components will remain unchanged or it will reduce by exactly 1. Either this will happen or this will happen. Okay, very simple. Either this will happen or this will happen. Now, the same question, let me ask for a strongly connected component. So you know the definition. A strongly connected component is maximal set of vertices such that any two vertices are strongly connected, mutually reachable. This is the definition of a strongly connected component. Okay. Now the question is saying that on adding one extra edge, an edge which is previously it did not exist, to directed graph, the number of strongly connected component, can it increase? Please tell me, can it increase? Is it possible that it can increase? It cannot increase. Very simple concept. You have a directed graph. Very simple. You have a directed graph G. in this directed graph G, let's assume let's assume number of strongly connected component. Let's assume that is 4. Let's assume you have 4 components. Okay, let's assume this is S1. Let's assume this is S2. This is S3. This is S4. Now, if you add one edge, for example, if you add one edge like this, okay, if you add one edge, whatever edge you add, can you increase the number of components? Like basically, if you add one edge, by adding one edge, will they become less connected? Will they become less connected by adding one edge? Can they become less connected? They cannot become less connected. Very simple. So if you add one edge, by adding one edge, they will not become less connected, right? Okay, adding one edge does not make it less connected. Adding one edge cannot. Adding one edge, you are adding extra. You are adding extra edge. So adding one edge does not make it less connected. Does not make it less connected. Less connected means strongly connected component cannot increase. Okay, does not make it less connected. Very simple. Okay, if you add one edge, then it will not make it less connected. I can say number of strongly connected component cannot increase. Cannot increase because you are adding one edge. Then it cannot increase. Okay, very simple. Now, what about this? So this, okay, cannot increase, that is fine. Okay, cannot increase. Cannot increase, this is correct. This is correct. Cannot increase. Very good. How much it can decrease? Can it remain unchanged? Tell me, can it remain unchanged? May remain unchanged. May remain unchanged. Is it possible? Can it remain unchanged? Yes, it can remain unchanged, right? Okay. Yes. So if you have a graph G plus one edge, then okay, you can notice that it can remain unchanged. Like for example, if you have this graph A, B, C, this graph, consider this graph G. In this graph, let me add one edge. In this graph, let's add one edge. Let's add BA edge. This edge, let's add edge BA. Okay, this BA, this edge, let's add. So let me add this edge. Means I am adding this edge. Now tell me, here what is the number of connected, strongly connected component? That is also 1. Here also 1 and here also 1. Okay, so it can remain unchanged, right? So here also 1, here also 1. You are adding one edge. This edge you are adding, this edge. Okay, very simple. So I can say that, yes, it can remain unchanged. May remain unchanged. Yes, correct. Can it reduce by more than 1? Cannot decrease by more than 1. Cannot decrease by more than 1. No. See, actually it can decrease by a lot. Okay, let me tell you, it can decrease a lot. Just consider this graph. Please consider this graph. Okay, consider this graph. A, B, C, D, E. Consider this graph. How many strongly connected components? Tell me how many strongly connected components? 5. How many strongly connected components? Total 5. Total 5 strongly connected components. Tell me which edge I add such that one edge I will add and it will become 1. It will come down to 1. It will come down to 1. See, it will come down to 1. Number of strongly connected component, it can become 1 very easily. Very easily you can make it 1. Very easily you can make it 1. This is your original graph. Your original graph is this. You can decrease A, B, C, D, E. This is your original graph. You can bring, okay, by adding one edge, just add one edge, it will bring down to 1. Just add one edge. Okay, just add one edge, it will bring down to 1. This edge you add, and now how many? Only 1. From 5 to 1. Only one edge I am adding. Can you make it 2? Can you make it 2? Which edge I add such that it will become 2? 2 components I will get, such that I will get 2 components. If I do this, then I will get 2 components. If I do this, How? Okay, I want three components. I want three components. In this graph, I want three components. Is it possible? In this graph, I want three components. Is it possible in this graph? C to E. C to E. No, this edge will not do. No, this edge will not do. C to E will not do. E to C. E to C. Yes, now I have three components. If I do, okay, if I do this E to C, now you can notice I have three components. This. Total three components you have. And here you can notice total two components you have. Very simple. So can you notice you can bring down to anything? Yes or no? Is this clear? You can bring down the number to anything. So cannot decrease by more, okay, more than one. No, it can. Cannot decrease by more than two. It can. Basically, it can go up to any number. Okay. Is this clear to everyone? Please tell me. So note. So remember, if you have a directed graph, if you have a directed graph G plus one is, okay, let's assume you have a directed graph G. In this directed graph G, let's assume number of strongly connected components is K. Okay, let's assume number of strongly connected component is K. Okay, now if you add one more edge, okay, you have this G in which number of strongly connected component is K. Now G plus one edge, if you do this, then number of strongly connected component, what can I say about them? They cannot increase. They cannot increase. So okay, they cannot increase, but they can decrease. They can never increase. If you add one edge, you are adding one edge, then they cannot increase, but they can decrease. They can decrease to 1. Is this clear? Please tell me, the concept is clear or not? So what happens when you add one edge? We have already seen. This we have seen. This we have seen. Okay, and this we have seen. Also this we have seen. These concepts we have seen. So this is your concept of strongly connected component. Please tell me, is this clear? Concept of strongly connected component. Anyone has any doubt in this? Crystal clear. Can I say crystal clear? Is it crystal clear? Okay, very good. So this is the definition. You can notice what is a strongly connected graph. A directed graph is strongly connected. When can I say a graph is strongly connected? Tell me, what do you think? A directed graph, you have a directed graph. When can I say this graph is strongly connected? When can I say this graph is strongly connected? When you have only one strongly connected component. Yes or no? Okay, when you only have one strongly connected component, I can say there is a path between every two vertices. Okay, every two vertices you take, every two vertices are strongly connected. Every two vertices are strongly connected. Every two vertices. So this is the definition of strongly connected directed graph. For directed graph, what is the strongly connected graph? Strongly connected directed graph. So when can I say a graph is strongly connected? I can say that very simple. You can use this definition. Number of strongly connected component is equal to 1. Okay, either you can use this definition, or you can use this definition, that every pair of vertices, any two vertices you take, every pair of vertices are strongly connected. Every pair of vertices are strongly connected. Every pair means number of strongly connected component will be 1. Okay. For example, this graph, if you notice, this graph is strongly connected. This graph is strongly connected. This graph is strongly connected. This graph is not strongly connected. What is the number of strongly connected component here? Number of strongly connected component 1. And what is the number of strongly connected component here? Number of, okay, so you can notice this is a cycle. So, okay, this is a strongly connected component. This is a strongly connected component. This is a strongly connected component. So this is 3. So the definition is very simple. Let's see this one. A, B, C. Is this strongly connected? Can I say this is strongly connected graph? Yes, this graph is strongly connected graph. SCG, strongly connected graph. Yes, this is strongly connected graph. Now you notice one more thing. This is also a strongly connected graph. This is also a strongly connected graph. Agree? In this graph is also a strongly connected graph. You can check it out. Okay. Next. This graph is also a strongly connected graph. All these graphs are strongly connected graph. Note. We think, we visualize. Remember, we visualize strongly connected component as a cycle, as a directed cycle, as a directed simple cycle. This is how we visualize. This is just a visualization. Okay, like if I say, for example, if I say that strongly connected component is this, A, B, C, D, then how can you visualize? How can you visualize this? You can visualize this like this. Like this you can visualize. Okay, are you getting my point? This is how we visualize. So we visualize this strongly connected component as a directed simple cycle. But remember, it need not be directed simple cycle. You can notice, for example, here also, this is also a strongly connected graph. Only one strongly connected component you have. One strongly connected component you have. Here also one strongly connected component. Here also one strongly connected component. Here also one strongly connected component. Okay, so very simple, these things. So this is how we visualize the strongly connected component. Okay, let's see this question. Please tell me everything. Like, is this, first of all, you tell me, is this strongly connected graph? This graph, is it strongly connected? So find number of strongly connected components. What that will be? Number of strongly connected component. How to find? Go systematic. Don't go random. If you will make mistake. Find strongly connected component of 0. Let's find out a strongly connected component of 0. So that will be 0, 1, 2, 3. That will be 0, 1, 2, 3, because there is a cycle. See, there is a cycle. So 0, 1, 2, 3. And you can notice that nothing else. So this is strongly connected component we got. Okay, we got this strongly connected component. Which is the strongly connected component of vertex 5? Vertex 5. That will be 5, 4, 6. You can notice that will be 5, 4, 6. So this is a strongly connected component. You can notice this is a cycle. This is a cycle. And this is another strongly connected component. Okay. So finally, this is also another. So finally, I can say number of strongly connected component is 3. Total 3 strongly connected components you have. So is this a strongly connected graph? Can I say this is a strongly connected graph? Is this a strongly connected graph? No, this is not a strongly connected graph. Let's see this one. How many? What is the number of strongly connected components? Quickly tell me. How many strongly connected components we have here? There are total 4. You can very easily see there are total 4. Okay, because you can notice this will be a component, this will be a component, this will be a component, this will be a component. Nothing else. So there are 4 components, strongly connected component. So this is also not a strongly connected graph. So everything we have seen. So remember, intuitively, we think of a strongly connected component as a cycle. Okay. So this is the complete thing that we have seen. Everything we have seen.